So last Friday, I arrived here in Perth for LCA, and I was feeling a little bit tired and jet-lagged. So I went off to my room at Trinity. It was getting a bit late, and I was stuffed, so I decided I just had to sleep. So I turned off the light, and it just went pitch black. Couldn't see a thing. So I was doing that thing where you're sort of shuffling around, trying not to bash your shins on anything. And I found the bed and lay down. I was just feeling exhausted. And opened my eyes, and after a few seconds, I realized that I could see stars, even though I was inside. Some previous resident had put luminous dots on the ceiling. And they'd even gone to the trouble to get the constellations correct. So for all of human history, the sky has been a source of inspiration for us. It's been a mystery, it's been unattainable, something that was out there. And it's always been above us. We've been stuck down here at the bottom of Earth's gravity well. It's only in the last few years that we've been able to step outside of the Earth and look at it from the outside and get a different perspective to what humanity has had for all of the time of our existence. Just a few months ago, Chris Hadfield came back from about 6 months on board the International Space Station. And he told a story about a moment when his perspective changed in relation to the way he saw the Earth. He was conducting a spacewalk, so he was outside the International Space Station, and from his perspective, his brain was telling him that the Earth was very solid. It was this big thing that was down below him, and it was below his feet, because he was interpreting what was coming through his eyes. And then he did a perspective shift, and all of a sudden it wasn't below him. He was floating in the universe. The ISS was over here. Earth was just something else that was floating over there. He'd achieved some level of mental disconnection from it, and it was no longer down. It was just something in the vastness of space. So we see that even more strongly if you look at images like this one, which was taken from Apollo 17 at a distance of about 35,000 kilometers as they were traveling to the moon. You can see the slender shell of the Earth, and how little there is around it that really supports life, and this is where we live. And Voyager, taking this photo 1.6 billion kilometers away from the Earth, looking back. So this is the original unscaled, full-resolution image that it took, looking back directly towards the Earth, which you can see, obviously. It's right there. So we'll zoom in a little bit, and just in case you still can't see it, it's that little dot there. So it's 0.12 of a pixel on this particular image. So given that space is such an inspiring thing, I mean, I'm a nerd, so I love technology. I love doing this sort of stuff. How many people here at some point in their lives have thought how cool it would be to work with space technology, getting something up into orbit? Okay, so I'm among friends. So a slightly tougher question. How many people here at some point have worked on a project that has or will go into space? Yeah, there are a few in the room. That's amazing. And that shows how special this audience is. But imagine the effect on our education system and on uptake of science, technology, engineering, and mathematics. If you could walk into the average high school science classroom and every single student put their hands up, now that would be an amazing thing. So how many people here have used Arduino? Okay, most of you have, but there are many who haven't. For those that haven't, Arduino is a tiny microcontroller board. It's about the size of a pack of playing cards. You can get it for $20, $30, $80, depending on the particular model. You plug it into your computer using USB, and you can make it connect to sensors, you can make it drive things, and it comes in a whole lot of different models. There's a reference design, which is all open hardware. You can get versions with built-in Ethernet if you want to do networking. A few years ago, some of you would have got the tiny USB thumb drive size Leo stick. Because it's open hardware, of course, you can do it yourself. So my remote controller is going crazy. So you can breadboard it if you want to. You can also get kits. So in one box, you have everything you need to do experiments with sensors and actuators. Some suckers have even written books about it, but I don't know why they would have done that. And there is a huge resource of expansion boards that can go onto it. So just about anything you can imagine in terms of connectivity, you can do with an Arduino. Now, what that has resulted in is a huge body of knowledge of how to use this platform. There are millions of people around the world who have worked with it. It's very commonly used in education, both in high schools and at university level, and including in space education. So this is Stephen Hobbs. This is a photo I took at the Australian Space Science Conference late last year. And his little Mars rover that he uses for education. It's got an Arduino brain, and it can drive autonomously and avoid obstacles. And it replicates the functionality of a Mars rover. So the thing is that space technology is generally very expensive, very inaccessible. How do we take the openness and the accessibility of Arduino and combine it with the mystery, I suppose, and the inspiration of space? So in 2012, 4 graduates of the International Space University got together and decided to take these two things and combine them. Most space projects are built with a very specific purpose in mind. They are optimized for a scientific outcome or to achieve some particular engineering test. But what they had in mind was instead to take the flexibility of Arduino and put it in orbit so that students could access it, just like they could use an Arduino sitting on their bench in the classroom. So they tested the concept by taking a number of Arduinos, connecting it up to a shared sensor suite, and proved that they could use a shared communications bus to talk to all of these sensors. Now, the way they chose to go about this was using a standard called the CubeSat standard. CubeSats have been growing rapidly in popularity over the last 10 years in particular. They originated in 1989 at Cal Poly. And the CubeSat standard stipulates that the satellite has to be a 10-centimetre cube under 1 1/3 kilos in mass. And there are a number of other restrictions on it as well. But by having a common format for a very small, very cheap satellite, it makes it possible for small groups of people to, with very little funding, build a satellite that can actually be placed into orbit. And by having a standardized form factor, it means that a lot of the infrastructure around it, like how do you actually get this into orbit, how do you then deploy it, can be standardized. So there have been quite a few CubeSats launched over the years. As of late 2013, there have been just under 100, I believe, that have been launched, including these 3. I showed this picture at the last LCA. This is 3 CubeSats being deployed from the International Space Station. And I particularly like this picture because it illustrates the flexibility of CubeSats in terms of having an idea for something that is not necessarily going to require a lot of funding, or it's not going to achieve a lot of funding, but it's still an interesting thing to do. If you look at the top right CubeSat there, that's a CubeSat called FitSat, which was made at the Fukuoka Institute of Technology in Japan. And this is a closer look at it. So FitSat, if you look at the top of it, all of those things are high-intensity LEDs. And the purpose of FitSat is to blink out Morse code messages as it flies across the sky. So it's a high-intensity blinking LED in space. So the ArduSat team had a plan for how they would use this CubeSat standard and incorporate a number of Arduinos into it and a range of sensors. But they needed funds for it. So, of course, they went to Kickstarter. And I think it was about a day or 2 days after this project went up that I saw it, and I thought, oh, space technology and Arduino, this is awesome, it's combined. I really got to get into this. So I contacted them and offered my services. And so I basically said, I'll do anything for you. Like, I'll give you your hardware or like make your coffee. So in the end, the agreement was that I would design the payload processor module, which is the part of the satellite that will run the experiments in space. So this was in June 2012. By September 2012, the team over in California had some test sensors put together. This is definitely not space ready, but it was just an initial integration to see how all of this would fit together. What you can see, that big funny shaped black thing there is it's called a spectruino. Basically, it's an optical instrument that allows you to measure different wavelengths and perform some interesting experiments. There's also a Geiger counter and a whole bunch of other things there. So September 2012, some basic hardware was put together. In October 2012, that then reached 85,000 feet under a high-altitude balloon flight, which was done in Colorado. And through November and December, I took the concept of compressing all of these Arduinos into a tiny little package and laid out a PCB, which ended up being this one right here. So January 2013, we had the initial hardware, and this is what I showed at the last LCA. This then did some testing. So this board has, well, you can see the size of it from here. This board essentially has 17 Arduinos on it. Each of those little rectangles is equivalent to an Arduino Uno. So it's an ATmega 328 with its associated supporting parts. And up the top is an ATmega 2561, which is like an Arduino Mega. So it's 16 nodes capable of conducting independent experiments, all accessing the sensors in the satellite, and then one as a supervisor, which can do software updates, which we'll get to in just a moment. However, there were some problems with this design. One of the things that I left off was a method for the supervisor to be able to reset any of the experiment nodes. It had control over their power, so my assumption was that it would be enough to simply power it down, power it back up if anything went wrong. But we found that it was also useful to be able to assert the reset line without power cycling. So that was one of the fixes that I made. And there were a couple of other minor changes that just made the board layout a bit better and made it easier for debugging purposes. So by February 2013, we had the revised design. March 2013, we had the actual hardware ready to go. So this is the flight-ready ArduSat payload processor module. And we fabricated 5 of these. So 2 of them are right here. One of them is currently in California in the ground station, and 2 of them right now are in orbit. So by June 2013, all of the hardware had been integrated. This photo was taken at JAXA in Japan. The person standing second from the left is Joel Spark. He's payload engineer for ArduSat. And here you can see a close-up of ArduSat 1 and ArduSat X. So these are the first 2 ArduSats that were ready to go into orbit. And in terms of size, they're about this big. So if you think a satellite is always the size of a truck, that's not necessarily the case. One of the interesting things about, or one of the obvious things about satellite technology is there is a very strong push to make it as small and light as possible, because that every gram you can save is a gram less that you have to get into orbit. So we then had ArduSat 1 and ArduSat X in June 2013 ready to launch, and all clean, they'd been set up ready to deploy. So then came one of the most surreal moments of my life. As I was sitting at home watching the NASA TV live stream.
3, 2, 1, ignition. And liftoff. Liftoff of the HTV on a journey to the International Space Station.
コウノトリ4号機を搭載した H2B ロケット4号機は平成25年8月4日午前4時48分46秒に種子島宇宙センターから打ち上げられました。
We had a liftoff of the H2B launch vehicle number 4 with the Konotori 4 on board from the Tanegashima Space Center at 4:48:46 a.m. on August 4, 2013, Japan Standard Time.
And 35 seconds into the flight, and the familiar scream of the HTV as it heads uphill.
総合司令塔に引き継がれています。
After liftoff, the launch vehicle operation.
So I think it was about 2 minutes after that that I remembered that I really should breathe. About 90 seconds after liftoff, HTV-4 was in orbit. So those things really move. There's a lot of power in them. It was on a low energy transfer to the International Space Station, so it took around 6 days to dock with the ISS. And the cargo on board the HTV-4 was then taken aboard the ISS. One of the things we had to do was wait for a Japanese flight engineer to be present on the ISS, and because the actual deployment took place from the Kibo experimental module, which is a Japanese experimental module. Now, the way the actual deployment happens, because CubeSats are cubes. They're designed for the most simple deployment mechanism possible. And basically, they're pushed out of a box by a spring. So what you see here is a device called a P-pod, which is a polypicosatellite orbital deployer. It's got a capacity for up to 3 CubeSats. So the hatch is opened, 3 CubeSats are stuffed inside. It's a bit like the magazine on a Nerf gun or something. The door is closed, and a solenoid can then release the hatch. So that particular, this isn't the P-pod that was used to launch ArduSat. The P-pod itself was preloaded with the satellites. And in this video, what you can see is flight engineer Koichi Wakata on board the ISS. So he is inside the Kibo experimental module, and in that plastic wrapper is the P-pod containing ArduSat 1, ArduSat X, and Pico Dragon, which is a CubeSat from Vietnam, I believe. And just behind him is a sled, which is mounted on rails inside the airlock. Now you can see that 2 of the P-pods have been mounted. You can just see the ends of them there. And the sled is retracting inside the airlock. They can do all of the preparation for these in comfort because they can just be doing this inside the Kibo module and then close the hatch. So everything is then prepared inside the airlock and isolated. You can see him bracing himself. So this is a view from the porch outside the Kibo module. You can see the external airlock door opening. And just inside that is the other end of the sled that we saw a moment ago. And on the end is a sort of cloverleaf grappling mechanism that is used to retrieve the sled. So the sled then comes out of the airlock, and GEM, which is the Japanese external manipulator arm, comes down and grapples the end of the sled, retracts it from the airlock, and then aligns it in the correct position to deploy into orbit. So Koichi then pressed the button that released the door, and off they go. So there were cameras at all different angles. This is a still photo that was taken from, I think it was from the cupola of the ISS. And this picture was named by Wired magazine as one of the most amazing space photos of 2013. You can see there the first 2, so the bottom left and the middle are ArduSat 1 and ArduSat X with Pico Dragon just behind. So once the satellites are in orbit, it's a little bit hard to stick in a USB cable and do any updates. One of the most important things about this whole project is being able to update experiments in flight. We don't want to have to just preload experiments on the ground and then have it run through a schedule. The best situation is if you can update experiments on the fly. So you might discover the results you're getting are not quite what you expected. You need to change your sample rates on sensors. There could be a whole lot of different reasons you want to update. So we want to be able to push new software to run on those experiment nodes while it's in flight. Now, from an end user's point of view, if you're a student at a high school in a science class and you've come up with an idea for an experiment, what you do is write the experiment using an online editor. It's based on the Codebender's IDE and integrated into a larger management console that lets you get information about the satellites. So it's designed to support multiple satellites. You can pick which one you're interested in and then create a new project just directly here in your browser. It has access to a whole lot of libraries built in that allow you to talk to the sensors, storage on the satellite, and all of the other things. So it also has a plugin that lets you talk to the serial port. So if you just have a regular Arduino, you can plug it into your laptop, and you can even have the exact same sensors as on the satellite sitting on your bench. And then once you're happy, you just click Begin Satellite Deployment. The code is uploaded to the satellite. There's a little bit of magic in there, which we'll talk about in a second. You can see the various projects that you have access to. And you can also, once projects are complete, you can download the data from that particular project as a CSV file, pull it into a spreadsheet. You can do visualizations, whatever you want with it. So from the end user's point of view, they are sitting there with an in-browser IDE, making up their experiment, and then getting the result back from the satellite that is executed in orbit directly in their browser. So you can conduct experiments in space without having to get up from your desk. What actually happens in terms of the process from clicking begin satellite deployment is that the code is sent via the internet to California, where it is inspected just to make sure that you're not going to do anything too nasty. And there is a functional duplicate of the satellite. And the code is executed on the satellite itself so that it can be finally checked over and we know that everything is doing what it should. And it is then transmitted back up to the flight computer on board the satellite and made available for distribution to one of the nodes. So if there are a whole lot of people who are wanting to run experiments on the satellite, then you need to have a queue of people who are using it. You need to know who's being given time, all of that sort of thing. So all of that is managed through the ground station in California. Now, in terms of the actual updates of what's running on the processor nodes, let's look at how that works. So the satellite itself has a bus called a CubeSat system bus, which is this big stacking connector running down one side. All of the modules in the satellite communicate through that bus, and that passes power, serial, I2C, a whole lot of other things as well. And the flight computer via that bus can talk to the supervisor node. So on the payload processor module, we have the supervisor node sitting up here, which has control over all of these experiment nodes. There is also an SD card on here. So the flight computer can send basically a new sketch. It says, here, take this sketch and run it on one of your nodes. It gets stored on the SD card, and then the supervisor picks one of the nodes. It decides which one is available, and it has control over the power rail for each node. And this is partly a power saving thing as well. So if any experiment nodes aren't in use, we don't want them sitting there burning power, so they just get totally powered down. So it starts up one of the nodes, and it also has control, it has connection through its second UART with the UART on board the processor node. So this is very similar to how you would program a regular Arduino with an IDE, just with the IDE and a USB cable plugged into it. It's just sending the data via the serial port. It uses a multiplexer. It's actually got two multiplexers, one for transmit and one for receive. So the UART connections from the supervisor go out to the pair of multiplexers, and from there they span out to all of the experiment nodes. It also has control over reset, and this is the thing I left out the first time around, but I learned from my mistakes. And that allows it to reset any of the nodes. So at this point, what the supervisor can do is basically pretend to be the IDE. And the IDE normally uses ArduSat to do the actual upload. So running on the supervisor for ArduSat is an operating system called FreeRTOS, which many of you may have used. It's an open source real-time operating system. And the AVR port for that is maintained by my friend Philip Stevens down in Melbourne that many of you may know as well. And it has a library in it which allows it to communicate with the flight computer. And it also has support for implementing the protocol necessary to reset the experiment node and then pretend to be ArduSat. And it just sends a new sketch to it. So each of these processor nodes that's running on here actually just thinks it's an Arduino Uno. It's running the standard unmodified bootloader. And part of my reason for doing that was to make the environment as similar as possible to what you can replicate at home for a few dollars just using off-the-shelf parts. I wanted to do everything possible to prevent any differences so that if you are testing something, you know that whatever works on there is going to work in orbit. I've had a lot of people say, why don't you just use FPGAs or something and run multiple virtual cores? And that's certainly a valid approach. But for this particular iteration with the first generation of ArduSat, I wanted to make the hardware as predictable as possible. So this was just the design decision that we took. Now there are 16 experiment nodes on here, not just one. So basically that whole thing is then just duplicated and then duplicated again. So it's not exactly rocket science, it's pretty easy doing that bit of it. Now, the next question is, how much is this going to cost? So it's obviously cost a lot to build the hardware. It's cost a lot to get it into orbit and get it deployed because I've never actually seen a bill for, you know, astronaut timesheets or anything, but I'm sure they're expensive. So the way the economics of this break down is that the satellite itself has a life expectancy probably around 4 to 6 months. That's because it can't maintain its orbit. It can control its attitude, so it can orient itself in different directions under control of the flight computer using a system called the Attitude Determination and Control System, or ADCS. And that's important for things like optical instruments where we need to be able to point in a specific direction to take a reading. It's also important in terms of communications because we want to keep antenna alignment correct. So we can run, say, between 12 and 15 experiments at any one particular time because some of the processor nodes won't be running. And if we allocate time in 1 week blocks, what that means is that we can give 1 week of experiment time on the satellite for under $300. So that's a price point which makes it accessible to a high school science class that does a bit of fundraising. All of a sudden, participating in space science isn't something that takes $100,000 to launch your own CubeSat. It's $300, and you can run an experiment in space. Now, there has been so much interest in this and such a huge take-up. There is an enormous waiting list that the current plan is to launch 30 ArduSats per year over the next 5 years. So what that equates to over that 5-year period is around 500,000 school kids who will directly participate in running experiments in space. So think for a moment about the impact that could have on people making the decision to go into any of the engineering or science-related fields. The satellites in orbit themselves are pretty cool, and being able to run experiments yourself just using off-the-shelf hardware is cool. But one of the things that I really set out to do right from the beginning of this project was to make the actual hardware available as well. Now, there are a few hurdles there. First, it's very expensive. So if you look at the typical stack to build a little satellite like this, you're up for many tens of thousands of dollars, which is not viable if you're a high school science class. So what I've been doing is progressively developing new modules to replace the expensive commercial parts with cheap open source parts. So one of the first modules I did was the prototyping module. And this was something that I did early on. I showed this at the last LCA. It's basically just like a prototyping shield, but for a satellite. And this is a satellite prototyping module in retail packaging. It allows you to do some interesting things, even just with a simple prototyping board like that. You can put together experiments and connect things together. So next I did the Arduino adapter module. And this is a way to quickly build up a little satellite stack by incorporating an off-the-shelf Arduino. It's basically like a big shield upside down. You take whatever Arduino you have, plug it in. There are breakouts for all of the Arduino I/O, breakouts for all of the CubeSat system bus I/O, and some prototyping area, and power supply pass-through jumpers. So with a few minutes of plugging things together, you can have yourself a fairly robust little stack that is quite functional, that you can do development using a familiar software environment, and get somewhere towards having a satellite analogous system. The next thing what really got me excited when I started working on it was actually the power supply module. And I promised it at the last LCA, and now I have it. So this module you see on the top here is the power supply for the satellite stack. It's got a lithium-ion battery that it can charge off USB, which is great if you're just doing experiments in the classroom. There is a DC input, so you can run solar cells into it, and it's wide-range input. I specifically set the input to take anything from 2.7 to 40 volts, because what that allows you to do is use it in a whole lot of different environments. And this sort of stuff is good not just for satellite-type projects. You could use this for industrial data logging or remote area sensing or whatever you want to do, which can be a really interesting thing to do with students. What you can do is get them to think about how to measure things in their environment and look at harsh environments like measuring soil moisture and temperature and sunlight and all of those sorts of things. So something like this can be used to run experiments with students under a high altitude balloon or out in a remote area. It has onboard charging, it has current sensing, so it can measure the current consumption, the current on either the USB or the solar input. It's got 5 volt and 3.3 volt outputs, and it can measure the current that's flowing through both of those. It's got an onboard processor with a battery fuel gauge, so it can report its status. And it even has Arduino headers on it, so you can plug in a shield if you want to. So you can use this just as a power supply, like a smart power supply, or it's really a complete Arduino in itself. Now that might seem pretty wasteful or unnecessary. Why would you put Arduino headers on something like this? But what that allows you to do in a school classroom situation is have flexibility in things like communications. So if you wanted to build a little test satellite stack to run in your classroom, you could put a Wi-Fi shield in here and have your satellite on the school Wi-Fi network and have students access it just from their laptops. Or perhaps you want to put on a 433 megahertz transceiver, so you could plug that in as well. So by having the expansion headers on there, you can use any of the readily available communications methods that you can already get for Arduino. Just plug it in and away you go. And of course, there is the payload processor module. So this is the board that flew in ArduSat. But there's a fair bit more to do from here. One of the big problems is releasing designs. This is actually quite a big problem. Anybody that works in the space industry, this is like dealing with the MPAA, but far worse. ITAR, which is the International Traffic in Arms Regulations legislation, lists satellite technology as a weapon. And that means that doing something as simple as publishing a design on GitHub can attract all sorts of nasty attention. So one of the hurdles that I have to navigate still is how to release these designs. And I know that there are people in the audience that have already been making good progress on this. Yes? Where did that come from? So I think that there's going to be some good progress on this over the coming months. And what I would really like to see sometime later this year is availability of designs for space-ready hardware or for space-analogous hardware that can be used in a classroom situation, so that it's not just a black box. It's something that students can see and they can look at how it works and understand it. And there are a whole lot of other things that need to be done as well. The flight computer, it looks like I might end up collaborating with the folks from University of New South Wales on a flight computer. They've been working on a satellite project for a number of years that has just come to the end of its life, and they're about to begin, that was BlueSat, and they're about to begin a new project which will be a successor to it. So we may end up developing the flight computer in the context of the successor to BlueSat. I also want to do a different sensor suite, which is specifically tuned for use in the classroom, because some sensors that you would use in a vacuum don't make sense on the ground and vice versa. I want a sensor suite that is really useful to students and lets them use their imaginations to measure the environment around them. And of course, educational material. Part of that is publishing the designs, but it's also a matter of understanding how all of this can fit into a school curriculum. Like how is it the teachers are going to use this? So there were a couple of teasers that I left you with at the end of the talk last year. Last time I showed you this, which is a photo of a propulsion system for a CubeSat. Now the interesting thing about this is that it uses water as a fuel, which is then electrolyzed using power from the solar panels, and then you get hydrogen and oxygen, and then you get fuel, and then you can propel the CubeSat. Now that was just a bit of a concept at the time, but during the year, the University of Michigan turned this into a Kickstarter and got funded. So they now have a project for a plasma thruster. And they're actually quite well progressed with it. Their modeling shows that by launching a CubeSat with a total mass, including the motor of around 5 kilos, which includes about 2.5 kilos of water, will give them enough propellant to reach Mars from Earth orbit. So that would be an interesting high school science project. what did you do today at school, Johnny? So thank you very much. I hope you found that interesting. Willie. Oh, sorry, there should be a microphone.
Is it reach Mars and stop again?
Wait, hold on. We've got a microphone coming.
I'll repeat the question. The question was, is that to reach Mars and keep going, or is it reach Mars and stop again? That largely depends on how well you aim it. Because you can do a gravity slingshot or capture and put it into orbit. Yes, there was another question. There is a problem with that. Yes, you can generate power. Oh, sorry, the question was, there is the idea that you can use the Earth's magnetic field, because the satellite is traveling through the field, use that to generate power, and then get propulsion that can take you somewhere else. The problem with taking energy by intersecting Earth's magnetic field, and this is actually done as a deorbit mechanism, not as a mechanism to get into higher orbit. The problem is that if you are taking energy from the Earth's magnetic field, you are trading your kinetic energy for some other form, and your orbit is going to fall. So it would be more likely to deorbit you rather than give you energy. Oh, generating solar power, that's quite different, yes. Yeah.
Hi, John.
Hi.
Did you have to do any hardening, hardware or software?
Here's one I prepared earlier. The short answer is no. The ArduSat is in low Earth orbit, which is it's at an altitude of around 400 to 450 kilometers, and it's reasonably well shielded in terms of radiation. And it's also it's got a fairly short life expectancy. If we wanted it to be up there for 5 years or 10 years, then you would need to use parts that are radiation hardened and probably shielding as well. Now, the whole issue of shielding is an interesting one. It doesn't necessarily work the way you think it does. What can happen is if you apply shielding, what that will do is decrease the energy of particles that are traveling through it, and it may simply slow them down enough to cause problems for you. So depending on the radiation profile of the environment you're in, adding shielding may make your situation worse. But the summary for the ArduSat project is no, that hasn't been a problem.
John. Just a question. Why do American trade regulations affect you? ITAR is a US regulation.
Treaties. Yeah. That's a painful subject that I won't go into right now, but there is a very similar defence export restriction list within Australia, and according to various treaties between Australia and the US, the contents of the list has to be aligned with the DFSG, which is the list used by the US government.
You mentioned the prototyping board in retail packaging. Does that mean we'll be able to just pop round to our local JCar and pick one up at some point in the future?
Quite possibly, yeah. I'm not quite sure whether JCar would carry it just on the basis of the low volume that it's likely to have, but yeah, you could just order one retail.
Hi, John. I'm a little bit confused on the sense of scale. Is that thing actually the payload?
Yes, this is the contents of the satellite. So the entire satellite fits within a 10 centimetre by 10 centimetre cube. What you're looking at here is the internals of the satellite, which is then placed within an aluminium chassis. So I probably even have a picture of that, but I won't pull it up right now. In fact, if we flip back, you can get a sense of scale by looking at right here. So here you can see 2 CubeSats sitting on the bench on the left, and that's actually ArduSat 1 and ArduSat X. So this is the internals of it.
Hi, John. Up here. The ArduSat stuff looks like it only has one manager. What happens when you want to update or something goes wrong with the manager?
The manager itself can't be updated. That's one of the design decisions, is you have to decide how much redundancy you're going to build in. And you could, it's very similar to the decision that you make when you're setting up a server farm. Like, do you replicate processes within the server and have one fail, or do you have 2 servers? So in this particular case, we've got 2 ArduSats.
Hi, John. What frequency does the upload occur on? What radio frequency?
It uses the amateur band, which is pretty common. It uses 2 meter and 70 centimeter for communications. It's running at 9600 bits a second, so it's quite a low data rate. Basically, it's like a slow modem connection. And both satellites are also transmitting a Morse beacon on 437 megahertz, I believe it is. About every 3 minutes, they transmit a message stating things like it's got their identifier and then their battery voltage and a couple of other things. So that can be used just for getting some basic information. You know the satellite's there and it's alive to some extent.
A number of 10-centimeter cubes in orbit unintentionally starts to look like a Brilliant Pebbles orbital vehicle killer system. And so my question is, it seems likely that someone is or will assert authority over launches of this type. Has that happened already?
It is already regulated. You can't simply set up a rocket in your backyard and send something up into space. Even if you had the capability of doing so, local government regulations would prevent you, basically because you're breaching their airspace. It'd be like building your own aeroplane and flying it without a license. You're just not allowed to. So the question was, the presence of the propulsion system brings up the possibility of someone hacking it to turn it into a weapon. I can't see any way that you could deorbit a CubeSat in a way that it would survive and be a problem. Orbital vehicle killer. Okay. Yeah. Theoretically possible, perhaps.
Hey, John. Very cool, of course. Thank you for that. Right here.
Oh.
One of you.
Hey, Mark.
Hiding in the front. Were those solar panels that you had around? And I'm not seeing what the antenna is to receive updates and send data back.
Yeah. You get a better view from this photo. So the solar panels are on the faces of the cube, and the antennas in this particular case are retracted. They're spring-loaded. They are dipole antennas. And there is a little deployment mechanism. You can see it just down in the bottom left of the front CubeSat, for example. So once it has deployed from the P-pod, the antennas are spring-loaded and they whip up.
Okay. And right now they launch them so that they will deorbit. They just put them in a non-stable orbit so they come down and burn, I take it, right?
It's not so much a matter of it being a deliberately unstable orbit. It's just that even at an altitude of 400, 450 kilometers, there is still enough there that there will be a very small amount of friction, and over a period of time, it will just deorbit.
And do you have to worry about encryption for sending updates?
Yeah, there is authentication on that. Yeah.
John, over here.
Sorry? I can't see much, too bright.
Difference between ArduSat 1 and ArduSat X, is it just redundancy?
Different applications, really, more than anything. The original ArduSat project, the dream had been to build one ArduSat, and then the scope has grown dramatically beyond that. There was also some investment. There were other groups that wanted to get involved. So the funds that were raised on Kickstarter, one of the benefits, if you backed it on Kickstarter, was run an experiment, so get some processing time. And multiple satellites are being launched so that they can cater to investors who want to run it as well.
Hi. Can you speak about some of the experiments that have been run on these, and can the public view the output from them, for example?
It's just a little bit too soon to speak about things that have actually run. They've been in orbit for a few weeks now, and unfortunately, if LCA had been maybe a week or two later, we could have had a bit more data to share with that. So they've just been going through diagnostics and making sure everything works. We don't have any information back yet about specific experiments. But I've seen a number of experiments that have been proposed to be run on it. And one, for example, is pointing the spectrometer at the sun while measuring radiation patterns and see if there's any correlation between solar flare activity and radiation. Also listening for radio signals that are over the horizon, which indicates that there's been some skip within the atmosphere, which may be indicative of a meteor trail. So basically detecting meteors in the atmosphere.
Hi. In addition to the gentleman's question down below me about security of decommissioned units, my concern is simply about the physical presence of the units floating around in space. Is there any awareness around a need to have some sort of even discussion around collecting these units after they're no longer in use, simply from a trash perspective?
Yes, that's a very well-known problem. It's been discussed at quite some length. There are a couple of aspects to that. One is that if a satellite is placed in low Earth orbit, its orbit will tend to decay anyway. So you don't need to actively do anything to remove it. It'll eventually just burn up in the atmosphere. There have been, I believe, 3 instances of satellites being destroyed while in space. One was a collision between a Galileo satellite and an Iridium satellite, something like that, I can't remember. And that created a fair bit of space junk because the satellites crashed into each other, and you get a bit of a cascade failure effect. So that creates more fragments that then potentially will create more collisions and eventually end up with a sky full of little bits of metal. There are people who model this sort of problem who argue that we're heading towards that situation at the moment. But other people who say, no, that's not going to happen until we have far more satellites. So in terms of active deorbiting, if you place a satellite, if you weren't just some hobbyist, you were a company like a telecommunications company, and you were putting up a TV satellite that was going to be out at 20,000 kilometres altitude or something, it's not going to it's not going to burn up in the Earth's atmosphere because the orbit is not going to degrade. There are various international treaties in place that require anyone that puts up a satellite to either deorbit it using some mechanism within a certain period of time, I think it's either 20 or 25 years, or to place it into what's called a graveyard orbit. So that will be a stable orbit, possibly at a Lagrange point or somewhere like that, so that it won't cause trouble for other satellites. But that is definitely a problem that people are very well aware of. There's a lot of work in that area.
Hi, John. How do you arbitrate access to the common sensors between the various 328s, and particularly if one experiment wants to configure a magnetometer as having a particular scaling factor or whatever, and calibrate it, it might need it for a fair period of time?
Sure. Unfortunately, there just has to be human intervention in that case. So when the jobs are being scheduled at ground control, there is a list of the jobs that are currently being run, and you can see which sensors are being used. So someone is manually looking at this and making sure that nobody is swamping the communications bus, or you don't have 2 people trying to reorient the satellite to point the spectrometer in different directions at the same time.
What's the best way to get Australian schools involved in this project?
I wish I knew. That's one of the next big challenges. So I've got proof of concept hardware. And the thing is that I've gone to a number of schools. I've spoken to quite a few teachers about this, and it only takes about a minute and showing them and explaining the concept, and they say, this is fantastic, we've got to have this. But that's just a one-to-one sort of thing. That's a real grassroots interest in it. The big question then is, how do you incorporate that at a higher level into into the curriculum. And I don't know how to answer that question.
Yeah. How does the CubeSat orient itself?
Hang on a second, there's another one I prepared earlier. Where are we at? That one. Yeah, so you saw some of the other questions that I always get. So there are a few different ways that you can control the orientation or the position of a satellite. There are two different aspects to it. One is called attitude, so that's the orientation, and the other is translation, so that's physically moving it, either changing its orbit, moving it in a different direction. ArduSat can't do translation, so whatever orbit it's in, it's basically floating along helpless, but it can control its attitude. So the simplest method is using a big fixed magnet. So in the case of FitSat, which is that big blinking LED, there is a neodymium magnet in the bottom of it, and the whole satellite just acts like a compass needle and orients itself against the Earth's magnetic field. So it just stays in a consistent position. So very low tech, but it works. You can also use magnetorquers, and this is what's on ArduSat. A magnetorquer is a coil, and there are 3 coils, so they're mounted behind the solar panels on 3 different axes. And then by energizing the coils in different ways, once again, you can react against the Earth's magnetic field, and the whole satellite can be spun and oriented in whatever direction you like, with about a plus or minus 5 degree pointing accuracy, which is sufficient for pointing optical instruments in the direction you want to point. Reaction wheels is another common method, so basically a motor with a weight on it, and reaction thrusters, but that requires propellant, so ArduSat doesn't have that.
John, you're talking about 50 satellites a year, which would be awesome. What kind of deployment mechanism do you have in mind? Because presumably some young person on the space station cranking stuff out the airlock isn't going to scale too well.
Probably a combination of that and dedicated launches. Because there is so much more interest in CubeSats now, there are companies, particularly launch companies, that are deliberately building launch capacity just for CubeSats. In previous years, CubeSats were considered third-class citizens. They would be taking up the $100 million satellite, and they might throw a few CubeSats out as they go. There are, as I said, there are just under 100 CubeSats that have been deployed in the 20-odd years or so that they've been around up until last year, with ArduSat deploying 30 a year. There is the QB50 constellation going up this year, so 50 CubeSats in one launch that'll be, oh, sorry, not this year, in 2015. And there are a whole lot of other projects as well. So we're at a bit of an inflection point where we're going from 100 over 20 years to, the next 100 is going to be in the next 12 to 15 months. So launch providers now are really focusing around providing capacity for this sort of mission.
What sort of price points are you looking at for these open source boards that you're working on for the CubeSats?
In terms of scale, I'm wanting in the order of hundreds of dollars, not many thousands or tens of thousands like on the commercial unit. So the whole idea is that this shouldn't cost you $10,000. This is, I'm sure it's got 17 Arduinos on one board, but it shouldn't be more than in the order of hundreds of dollars.
As far as getting it into schools, you're saying it's a one-on-one process, holding up a piece of kit and inspiring somebody, and you can't release all the bits yet because of black helicopters. Can you do a mock-up and, this is exactly what it's going to look like, and you can be inspired looking at it, and then...
I can certainly build functional equivalents, so that's what I'm working towards now. So right now, the big missing piece is the sensor suite. So I have the power supply, I have the processor module, so I can run experiments, but I don't have the terrestrial sensor suite for use in the classroom. And there are a couple more pieces like that I want to put together, and then I can go around and really show people a fully working system. So I'm not saying that one-to-one is the best way to do it. I'm saying that this is just how I've been gauging interest so far, because I've been excited about this. So I've been going around talking to people and saying, hey, check this out. And they go, wow, that's awesome.
G'day, John.
Hey,
so
Tom.
what's the waiting list for a school if they wanted to get involved?
Right now it's kind of long because there's been so much interest. But hopefully once the rate of launches increases, that list will decrease quite rapidly.
Okay, thank you.
Hi, John.
Can you give a rough idea of the situation with power? How much input do you get from the panels? How much does the Arduinos consume? And is it really tight, or are you pretty comfortable?
Power budget is a big issue. I remember last year when B-Dale heard what the power budget was for it, he snorted and thought that was rather ridiculous. So ArduSat 1 and X are not necessarily very efficient. One of the trade-offs is because we've got multiple MCUs, they're running at 5 volts, they're using a little bit of power. So the short answer is that power budget is really important. You have to keep it as tight as possible, which is why we want to be able to shut down nodes when they're not in use. And some sensors also require a bit of power as well, so you don't necessarily want to run those sensors continuously. In terms of the actual power profile, the orbit, in low Earth orbit, it takes approximately 90 to 92 minutes to circumnavigate the Earth. So it's at an altitude of around 450 kilometers, which means it spends about half that time in daylight, so it'll be charging from the solar cells, and then about half that time in darkness, so running off battery. So essentially you have 45 minutes to charge, 45 minutes to discharge, and the battery provides enough capacity to run the satellite through that dark part of the phase.
All right, just to take the base of the slide you flicked past, how do you keep it cool up there? Because even though it's very cold in space, you do have the heat of the sun not being absorbed by the atmosphere, and you can't cool to the atmosphere.
Yeah, so there are 3 different ways that you can move energy around in the form of heat. So conduction, convection, and radiation. Within the satellite structure itself, you've got conduction, so it'll physically pass through the structure. Radiation, so you can take on heat by radiation, you can also lose heat by radiation, but there is no convection, obviously, because there's no atmosphere. Now, in terms of the way these are thermally modeled, because the satellite is physically quite small and it has very good thermal conduction through the chassis, it can basically be modeled as a single point. So the standard model that's used, I think, is a 10 centimetre steel plate, which means that you get very good conduction across the whole surface, and you get minimal hot and cold spots. But that said, when it's in the daylight side of its cycle, it will be heating up really fast. And the thermal profile that it goes through over the space of an orbit, it tops out at around 80 degrees or so, and then as it goes through the dark side, it radiates, loses heat, and it bottoms out at about -40. So it's being slammed from -40 to +80 degrees every hour and a half. The structure itself is designed to maximize thermal conduction through it so that you don't end up with hot and cold spots and the chassis twisting out of shape. The interesting thing is that that particular thermal profile pretty much perfectly corresponds to the ratings on, the standard industrial ratings on electronic parts.
You said that the satellite was about 450 kilometres orbit around Earth, and you also mentioned Lagrange points. Does the moon have a magnetic field in the same sort of way the Earth does? And you can see where I'm going with that? No.
No, the Earth's magnetic field, I think, is from the molten core, whereas the moon doesn't have a magnetic field.
So what's the possibility of getting things into the Lagrange points around the Earth, moon?
The Lagrange points are all based on gravity, not magnetic field. So it's the point at which multiple forces from gravity cancel each other out. And if you have a very large body and a very small body close to each other, the Lagrange point will be closer to the smaller body. But there are multiple locations. It's kind of a complex geometry, but there are different Lagrange points around any multi-body system.
All right, that's all we've got time for this morning. So thank you very much. We can give a huge round of applause.